All right, let's dive into two really fundamental ideas in thermodynamics, Cp and Cv. Now, these aren't just random letters. They are the key to unlocking a really interesting question. Why does it sometimes take way more energy to heat something up than other times? Let's get into it.
So, let's start with a puzzle you can picture in your own kitchen. Imagine you're heating up some gas. Why on earth would it take more energy to raise its temperature in an open pot than it would in a completely sealed one? I mean, intuitively, it feels like it should be the same, right? Heat is heat. Well, by the end of this, you're going to know exactly why that's not the case at all.
So here's our game plan. First, we'll look at the two main ways you can heat a gas. Then, we're going to see what happens when we trap it, constant volume, versus what happens when we let it expand at constant pressure. And that comparison, that's going to solve the whole mystery. We'll even see when this big difference just disappears.
Okay, section 1. 2 ways to heat. The big idea here is simple, but it is so powerful. When we're talking about gases, it's not just about pumping in energy. The conditions you create while you're doing it, well, they change everything.
You add heat, temperature goes up. That's pretty basic stuff. But for gases, we immediately hit this fork in the road. Are we heating the gas inside a rigid, sealed container where the volume can't change? Or are we heating it in something like a cylinder with a movable piston where the pressure stays the same? It turns out that single choice completely changes the outcome.
Let's start with the simpler path on that fork in the road, constant volume. Just picture a gas trapped in a super strong sealed box. It can't get any bigger or smaller. This is the world of Cv, the specific heat at constant volume.
Okay, so technically speaking, Cv is all about how a substance's internal energy changes with temperature. And what's internal energy? Well, just think of it as all the kinetic energy of those little gas molecules buzzing and bouncing around. The cool thing about this definition is that it tells us that when the volume is locked, the heat we add is directly tied to this very fundamental energy state.
So what does that equation times really mean in plain English? Think about it. The gas is trapped. It can't expand, so it can't push on anything, it can't do any work. This means that every single joule of heat energy you pump into that box has only one job and one job only, to make the molecules move faster, which we feel as a rise in temperature. It's super efficient. All right, now for scenario number 2. What happens if we take the lid off the box? Or better yet, replace it with a piston that can move up and down to keep the pressure the same. Now we're in the world of Cp, the specific heat at constant pressure. The definition for C sub HP looks pretty similar at first glance, but there's a huge difference hiding in there. Instead of internal energy, we're talking about something called enthalpy. Now, don't let the word scare you. Just think of enthalpy as the total package. It includes the internal energy, plus the energy the gas needs to basically push the rest of the world out of the way to make space for itself.
And this is where things get interesting. As you heat the gas, it wants to expand. And to keep that pressure constant, the piston has to move up. But pushing that piston, that takes energy. That's mechanical work. So now the heat energy you add is being split. It has 2 jobs to do. Job 1, raise the internal energy, just like before. And job 2, provide the energy to do the work of pushing that piston.
And right there, that's it. We can now bring it all together and solve the mystery from the beginning. Why is C sub V always greater than C sub V for a gas? It all boils down to that extra job.
Just look at them side by side. In the constant volume case, 100% of your energy goes straight into raising the temperature. But in the constant pressure case, some of that energy gets skimmed off the top to do work. It's like an expansion tax. So to get that same 1-degree temperature rise, you have to pump in more total energy to begin with to cover both the temperature and the work.
And what's really cool is that this physical reality is captured in this beautifully simple little equation. For an ideal gas, the difference between Cp and Cv isn't some random number. It's exactly equal to R, the specific gas constant. So here's the kicker. That gas constant R is always a positive number. Always. Which means this equation is basically a mathematical guarantee that Cp has to be bigger than Cv. It's not just something we observe, it's a fundamental law of thermodynamics.
You know, this relationship is so important that engineers and scientists gave the ratio of C sub P to C sub V its own special name. K, the specific heat ratio. And this little number is absolutely critical. It shows up everywhere in things like designing jet engines or understanding rocket nozzles, anywhere you have high-speed compressible gases.
Okay, so if this difference is such a big deal for gases, is it always a big deal? Well, no. And looking at the exceptions actually makes the rule even clearer. For things like liquids and solids, it turns out that CP and CV are almost exactly the same. And why is that? Well, because they're basically incompressible. Think about it. If you heat up a block of aluminum or a glass of water, does its volume change much? Not really. And if there's no real change in volume, there's no expansion, which means there's almost no work being done. That expansion tax we talked about, for solids and liquids, it's practically zero.
And that right there is the single biggest takeaway. If you remember one thing, remember this. The entire difference between C sub P and C sub V boils down to the energy cost of expansion. For gases, which love to expand, that cost is huge. For liquids and solids, which barely expand at all, that cost is so small we can usually just ignore it. It really is all about the work.
So that leaves us with a final thought to chew on. If this principle, the work of expansion, is so incredibly fundamental on this small scale, just think about how it scales up. How does this idea affect the efficiency of a car engine, which is literally all about harnessing the work from expanding gas? Or what about the massive atmospheric systems that create our weather patterns? The same physics that explains heating a pot on your stove is also shaping our entire planet.